Hi, ladies and gentlemen. We're going to take a look at some more information about the four fundamental subspaces. Today, we do not have a text reference, so that's going to make this lesson a little bit different than everything that we have done previously. The video is all of the content that is required. There's a lot in here. We're going to take a look at some review material, take a look at things we've already learned previously. We're going to spiral that information into some new and different ways to look at the four fundamental subspaces, and most specifically, to look at the bases for each of the fundamental subspaces. So let me start right off with MATLAB. And what we're going to do, this is our test case matrix right here. And what I'm going to do is just run the RREF. We know the RREF is going to give us critical information, things such as what are the pivot columns and what are some of the bases. We get that information right off the bat. We'll also take a look at a complete walkthrough on how to build the basis for the null space. So this is going to be our run right here. Let me just orient you. We have the A matrix here. I've echoed that back. And then I've run two RREF programs. One of them is my RREF program, very similar to what you did for project number one. You're going to need to use the RREF that you created for project number one when we are looking at finding the basis for the left null space. More on that later. And then I've also run MATLAB's RREF down here. And what I want to show you is the difference between my calculations and MATLAB's calculation. What MATLAB does, and we're going to take a look at the script in just a minute, what MATLAB does is it takes a look at the where we have the zeros, and instead of doing the actual calculations, it simply dumps zeros in. The RREF in MATLAB is designed to make pretty looking output when we give it integers or small fractions for inputs. It wants to show us something that looks nice as opposed to something that's accurate. And there will be more on that later. Let me just pull up MATLAB's, right? So here's the actual MATLAB command window, and I'm just going to type edit RREF. So you may not know that you can do this, but you can just jump in and edit any one of the programs that's in MATLAB. Don't do that, right? You will end up changing your functions in your MATLAB, but you can do it is the point. So we can take a look at how MATLAB builds the RREF. And it's not a long program. That's it right there, 66 lines. But what we notice in the beginning here is it says, does it appear that the elements of A are ratios of small integers? So it takes a look at whether or not the entries are integer entries or, like I said, simple fractions. If it is, then it changes the way in which it does the calculations in here. And the result is something that looks pretty, but is not as accurate. So that's a capacity for something that we just have to be aware of when we use the RREF. We're going to end up modifying our RREFs from project one, but we'll talk more about that later. So here's the RREF, and what I want to do now is take a look at what we already know when it comes to finding the four fundamental subspaces, specifically when we are looking for the bases. So first things first, step one in this process is really to realize that A is a linear mapping. We've talked about this, but it's important to realize. We have the dimensions of A are 7 by 5. So we know that A is mapping R5 to R7. And that's the first thing that we're going to put into our diagram here. We are mapping R5 to R7. So the input vectors are length 5 and the output vectors are length 7. From that information, really the second thing that we're going to look at are the dimensions. So, and it's really the dimensions of the subspaces. And we talked about this already. Strang covers this early in chapter 3. And so we know that we have the rank is the dimension of the column space and the row space. Before we make that note, though, let's review. The red, remember, is associated with the matrix A. I have the null space of A on one side, and I have the column space of A on the other. So the null space, you remember, that's all the vectors that get mapped over here to 0. And then the column space, of course, is the range, if you will, of the linear transformation defined by A and the matrix multiplication. Similarly, we have the green. We have the null space of A transpose, that's the left null space. And we have the row space, which is also the column space of A transpose. And the null space here, of course, works the same way. All of this stuff gets mapped over to the 0 vector in R5. All right, so let's take a look at the dimensions of these spaces. We know that from the RREF, we can calculate the rank. What we're looking for are the pivot columns. So I have a pivot column here and a pivot column here. Those two pivot columns means that the rank is equal to 2. So we already know the rank of A is equal to 2. And from that, we know that the dimension over here is 2 and over here is 2. Then the rest of what we've already learned from chapter 3 is that whatever the dimension of the column space A, of A is, that the null space of A transpose, the left null space, that has to sum to the dimension of the output space. So what we know is that we have to total 7. Well, we already have 2 accounted for in the column space, which means the dimension of the null space, the left null space, is 5. Similarly, the null space on the input side has to give us enough dimension to get up to 5. So we have 2 for the row space, and that leaves us 3 for the null space. That's all information that we've covered. And now we're going to move on to take a look at the bases. So the column space of A, that's equal to the span of, and how do I determine what this span is going to be? It's from the pivot columns. I know that I take the pivot columns from the RREF and I go back to the original A matrix and I grab those columns. I'm not going to rewrite them, but these are the pivot columns associated with the pivots that we found over here in the RREF. And so it's A1 and A3. Those two vectors form a basis for the column space of A. What about for the row space, the column space of A transpose? So the column space of A transpose, that comes directly from the RREF. Because the Gauss-Jordan elimination that we have done is really just row operations, which are linear combinations of the rows. We haven't changed the space that is spanned by the rows. All we've really done is eliminated the redundancy. What's in here that we can't tell right off the bat, but is obvious from the RREF, is that 5 of these 7 rows are redundant. They are linear combinations of the other rows. So the RREF reduces all of that redundancy down, creating 0 rows, and the result is 2 row vectors that span the row space. So these 2 vectors right here are the 2 vectors that span the row space. So this is really equal to the span of, and now I will write these out, these are vectors in R5, right? These are row space vectors, and they are 1, -3, 0, 2, 4, and the other vector is 0, 0, 1, -3, -4. Those vectors are a basis for the row space. That information comes straight from the RREF. What's next then is to consider the null space of A transpose. And let me move the null space of A. Let me move the row space over just a second. All right, so what we're going to find now is the basis for the null space. We've done this before, but I want to walk through this to show you a systematic way of doing it. Remember, all we're doing is what Strang has described as determining the special solutions. So the null space of A is equal to the span of how many vectors and where do these vectors live? Well, I'm going to switch over to the green. The null space comes from the non-pivot columns. These are the free variables associated with AX equals 0. That's what the definition of the null space is. It's the set of vectors that solves AX equals 0. So it makes sense that they come directly from the free variables. The free variables are in green there. What we have is we have vectors that live in R5. We see that over here. The null space is on the input side. And so we have 3 vectors from R5. And I'm just going to write them down in a general form just to show you how we're going to determine these in a systematic way that follows along with what Strang does. So Strang calls these special solutions 1, 2, and 3 respectively. What we're going to do is actually construct them in a systematic manner. What I want to do, just to give you an idea of how this works, each of these vectors here is in R5. And I'm going to highlight that by breaking them out. So they each have 5 entries. And I am going to split them up so that we can more easily see those 5 entries. Something just like this. So each vector here has 5 locations for numbers. What we want to now do is mark which of these components, which of these variables, if you will, are the free variables. So remember, we have multiplication by x over here. And when we multiply, the x2, x4, and x5 are the free variables, and that's what we want to highlight. The second entry and the fourth entry and the fifth entry are the free variable entries. Then how does Strang proceed? He says, well, we'll do this systematically by picking one of the free variables to be 1 and then putting zeros in for the other 2. And he just goes through doing that. So x4 is 1, and x2 and x5 are 0. And then finally, x5 is 1, and x2 and x4 are both 0. So the way we finish this up then, we have 2 entries for each one of these. And those 2 entries come from the 2 fixed variables we have. Now, we could write out the equations. We're not doing that. I'm showing you a more straightforward kind of systematic way to do this with the matrix. But you can always write out the equations. That's no problem at all. What we're going to do is we're going to take a look at the information that's in each of the columns that are non-pivot columns. So we're going to take a look at that piece of information, this one here, and this one here. These are the pieces of information that Strang refers to as the F matrix. And all we're going to do is fill them in the correct location. So for the x2 variable being 1, we use the second column. And we're going to take the negative of all the entries. So the negative 3, 0 becomes a positive 3, 0. And then we're going to move to where the x4 free variable is equal to 1, and that's the 4th column. And then we have a negative 2, 3. Remember, we're taking the negative of the entries. And then finally, for x5, we have a negative 4, 4. And so it looks a little bit silly because I've mixed the red and green colors together, but we have literally found the 3 special solution vectors. And those 3 vectors form the basis for the null space. All of that information is available from the RREF. We're able to find the basis for the column space, the row space, and the null space without very much effort. What's left out here that we have not yet addressed is the columns up, the null space rather, of a transpose. So we are after the information about the left null space. What is this thing equal to? This is information that we cannot derive directly from the RREF. Now listen, there are a couple ways that we could do this, but they're all computationally expensive. And when we're solving real world problems, we don't want to go down the road of spending the computational time to do this. We could just take the transpose of the matrix and redo the RREF. That's an expensive way to do it because we have to do 2 RREFs. MATLAB has a null command. Using the null command, we can find a basis for the null space. That's a very expensive computation. That involves finding the singular value decomposition, which is okay when we're going to use the information from the singular value decomposition, which is really valuable to us. But just to find null space vectors, that's a waste. And we would never do it that way. So what we'd like to do is we would like to run the RREF one time and be able to gather the information that we need for the null space of A transpose. We're going to do a little bit of a review of things that we've talked about previously in chapter 2, and we're going to enlighten ourselves to something that is very fascinating and clever. Let me move forward here a second. Let me remind you of something that we did in chapter 2. Remember, to find the inverse of A, we took the A matrix and we augmented with the identity. And when we ran the RREF on this, we ended up with, if A was invertible, if it was invertible, we ended up with the identity over here and A inverse. And that's great. This only works if A is square. What happens if A is singular or if A is rectangular? So if it's singular, or A is m by n, where m and n are not necessarily equal to each other, then what does this process give us? Well, to answer that question, what we're going to do is review a little bit about what Gaussian elimination is. Remember, Gaussian elimination is nothing more than applying our 3-row operations. Let me write them down for a refresher. All right, these are the 3-row operations right here. We can swap rows. That's just swapping equations. We can multiply a row by a scalar, which is just multiplying one equation on both sides by a scalar, or we can add a multiple of one row to another row. And that's just multiplying one equation by a number and adding it to another equation, exactly the type of thing that you've been doing for a long time to solve systems of equations. And all Gaussian elimination does, and really Gauss-Jordan elimination, is it systematically does this rapidly so that we can easily solve large systems of equations. What I want to do is remind you a little bit about how this works with the matrices. We talked a lot about the elementary matrices. Strang references this heavily in chapter 2. So let's go back and think about, how did we do row swaps with a matrix? We used permutation matrices, right? So these were permutations. And if you remember, what we did is we started with the identity matrix, and all of my examples, I'll use the 3x3 identity matrix. We started with the identity matrix. And if what we wanted to do was swap the first and third rows, we would swap the first and third rows in the identity matrix, and then we would left multiply by the resulting matrix. When we multiply by this matrix on the left, and then we sweep through, and we do exactly the row swaps that we want to do. What about multiplying by a scalar? I could start with the identity matrix, and then I could change it, and I could multiply, for example, the second row by 1/2. If I multiply the identity matrix, second row, by 1/2, I end up with this matrix. And again, if I left multiply by that matrix, when I sweep through, the second row is going to be multiplied by 1/2. The thing that I want to do for row operations is the thing that I actually do to the identity matrix before I left multiply by it. Remember from the elimination matrices, I could start with, and we only talked about this one time, but it bears repeating. I could start with the identity, and then let's say that I want to take -3 times the first row and add it to the third row. I could just do that with the identity matrix. I could take -3 times the first row, and then I could add -3 times the first row to the third row, and I would end up with this. And you know that this is the elimination matrix A31 if I'm eliminating a number equal to 3 down in that 3-1 position. The point of this is, every one of the elementary row operations is something that I can do with a matrix. Moreover, I create the correct matrix for left multiplication by doing the thing that I want to do to the identity. This is critical because what are we doing here? If we execute row operations on A, only A, and that's really important, and it's going to get into why we're going to use the RREFs that we created. If I execute the row operations on A, I am executing the same row operations on the identity matrix. And what does that give me? When I execute the row operations on A, and now I'm talking Gauss-Jordan elimination, not just Gaussian elimination like we did previously. If I run Gauss-Jordan elimination, I'm going to end up with R naught in place of A. This is going to give me the RREF. And what happens to I is it carries all the knowledge of the elimination steps that we did, because we've executed all of those things onto an identity matrix. So the result of performing RREF on the A matrix only is that we end up with the correct RREF, 0 rows included, and we get the record of what it is that we did via the elimination matrix. This is exactly the elimination matrix, such that if we multiply E times A, we get the RREF. We've talked about this before. We would never do this multiplication. However, the information is contained inside of that matrix. We have taken the identity matrix and converted it into the complete elimination matrix that gives us the RREF. Let me demonstrate this for you. So I'm back here at the MATLAB that we were doing. We executed the RREF on this. And now what I'm going to do is I'm going to augment with the identity. Let me just run this through and I'll walk you through what I've done. Here's the A matrix and I've augmented with the identity. Then I executed my RREF, and I'm going to just close this down so we can see the outputs more clearly. And we can see that what we have here is the RREF, because I've only executed the RREF on the original A matrix. I didn't continue executing it into the identity. And so the result is, sorry, let me get off of that. So the result is that I have the RREF here, and then this is the E matrix, and I've pulled that E matrix out. This is a record of everything that was done for the Gauss-Jordan elimination to create the RREF. To demonstrate that, I do an RREF check. I actually multiply the elimination matrix times A, which I would never do in real life, but I'm doing this to verify that this is true. And when I do the multiplication, what I end up with is I end up with the RREF matrix. Now, there are numbers in here that are non-zero because of round-off. Whenever we do double precision arithmetic in the computer, we run the risk of having round-off errors, and that's what we have. But you can see that the 1, -3, 1, 2, -3, 4, -4, that information is all correct. That's the RREF. All the rest of these numbers are due to round-off error. We can't use MATLAB's RREF to do this. We cannot use MATLAB's RREF to do this. What does MATLAB's RREF do? Well, right here you see the RREF exactly as we want for the A matrix. The problem is MATLAB doesn't know to stop. It says, wait, there's more matrix left. I'm going to keep going. And so all of these columns were linearly independent, so it makes them all pivot columns. That's not what we want. That means the RREF has actually run into the elimination matrix that we're trying to preserve and has wiped it out. We need to use our RREF, which we can stop after we've gone through the columns of the original A without having to worry about it continuing on through the appended identity matrix. So this is not going to work for MATLAB's RREF. That's why we have to use ours. And this is a very common theme. I know you love to use the built-in functions for Python, for R, for MATLAB, and that's great. And 99% of the time, that's going to work perfectly fine. But sometimes we have to understand what's going on well enough to be able to create our own so that we can do what we want to do. And this is one of those situations. We want to stop executing the RREF after we reach the size of the original A matrix. We don't want to continue on into the appended identity matrix. MATLAB automatically just continues on. So let me just show you for completeness sake what we're talking about with respect to accuracy. Here's the original A matrix. Here's the reconstruction of the A matrix using the elimination matrix that I have along with the RREF. I get this. This is MATLAB's recreation. You'll notice that it is not nearly as accurate. It has significant errors. These numbers should match exactly with these numbers because we have gone in and multiplied inverse of E times the RREF, which should give us exactly A. And in my version, in the version you built for project 1, that's pretty close. MATLAB's version is not close. It's not built for accuracy when we're using integer or simple fractions as inputs. All right, so what does that mean for us? Let's go back and take a look at this. So the A's that I was testing, just so you're clear, I was using this relationship, and then I was using A is equal to E inverse R naught. And I should be able to, from the inverse of the E, reconstruct A perfectly, or within round-off error. And for ours, that'll work, and for MATLAB's, that will not work. So why is this important to us? How is this helping us with the left null space? Let me finish the explanation, and then we'll be on it. So this is the important item here. After we do the RREF through the A matrix, we end up with this. And this ends up giving us the very important EA is equal to R naught. That's the E elimination matrix that we have. It includes all the permutations. It includes all of the changing of the pivots to leading ones. It's all in there. Let's break this down and take a look at it with larger matrices. So here's my A here, my E. This is my E matrix. Here's my A matrix. And then here's my RREF. So remember, the RREF in general has some zero rows. So I am going to make a division here. And let me just do it here. And I'm going to say that this is the R matrix. And then down here, I have a couple of zero rows. Then I'm going to move that split over to the E. And I'm going to, for simplicity's sake, just call this E top and E bottom, where I've just split it across the rows that match up with the zero rows in the RREF. Let's think about what's happening here. If I grab any one of these rows, so if I grab this row right here, what am I doing with that elimination row? I'm sweeping through A. I'm taking linear combinations of the rows of A, and I am creating the first row of the RREF. Similarly, when I come down here and grab the second row of the elimination matrix and I sweep through the rows of A, I'm taking all the linear combinations of A such that I get the second row of the RREF. And now maybe some of you see it. What that means is when I come down here and I grab this row and I sweep through A, what I find, that's equal to 0. I have found some vector, which is a row out of the elimination matrix, such that when I multiply it by A on the left-hand side, I find a vector that's in the left null space. In fact, however many rows I have in my elimination matrix, which line up with 0 rows in the RREF, those are all the vectors that form a basis for the left null space. That's where we're going to get the basis for the left null space. So going back to asking the question, how do I get the left null space? This is equal to the span of whatever the rows are in E that match up with the rows of zeros in the RREF. We talked about this when we talked about dimensionality. Let me back up for a second. We said that we can tell from the RREF with these 5 zero rows that we have a dimension of 5 in the left null space. We need 5 linearly independent vectors to create a basis for the left null space. we would end up with 5 vectors in here. Those would be the vectors, these rows, right? And I'm not sure how I want to designate this. I'll do it with the same color, but these are the rows of E that line up with the 0 rows in the RREF. Quickly go back to the MATLAB example. So in the MATLAB example, here's our elimination matrix. And if we start at the bottom and count up 5 vectors, those 5 vectors, which are our 7 vectors, those 5 vectors are the basis for the null space. And you can tell just by looking at the locations of the ones, they're linearly independent vectors. That's how we can find the left null space with one execution of the RREF. This is what we're going to do. So let's take a look at the problems we have for today. All right, so I just grabbed those and threw them up. So these are the problems we're talking about here. You're going to go through and basically execute exactly what I demonstrated in this video. You're going to write down the dimensions. You're going to have those graphics for the 4 fundamental subspaces. You're going to write down the dimensions, and then you're going to modify your Project One RREF code so that it will run on the A matrix, but you're going to augment an identity matrix in there so that you can capture the information about how the elimination is being done. And then from that, you'll be able to find the null space of A transpose. You're going to work on this matrix and this matrix. Those are the 2 participation problems. It'll take you, well, I mean, a little bit of work. All you have to do to change your code for the RREF is make it so that you take in whatever the A is and you augment it with an identity matrix that is square, of course, that has the same number of rows as the A matrix. Thanks very much, and we'll see you in class.